Here we're looking at a circuit where we have a charged capacitor and a switch and a resistor. This switch is going to close, and when it does, it will complete the circuit. It will create a path from one capacitor plate to the other, and the capacitor will begin to discharge through that resistor. When we have a circuit that consists of resistors and capacitors, we have what's called an RC circuit, RC for resistors and capacitors. We want to know how a circuit like this will behave. We want to know the current through the circuit, the voltage across the capacitor or across the resistor as a function of time after the switch has been closed and the capacitor begins to discharge. As long as the switch is open, there's nowhere for the charge on the capacitor to go. This positive charge is happy to be near the negative charge. There's no way for it to escape, so it will just stay there. Recall that a capacitor is a passive element. It doesn't provide energy on its own, but it's able to store energy that it must have gotten at some point previously from a voltage source, for example. So there's charge built up on the capacitor plates, there's a voltage across that capacitor as a result, and both of those are related to that energy stored inside the capacitor. And as long as the switch is open, that energy will simply stay stored. Once the switch is closed, now there's a path from one capacitor plate to the other. And so following our conventional current, we'll say that the positive charges will leave the positive plate of the capacitor, they'll flow through the resistor and down to the negative plate of the capacitor where they will reunite with their counterparts. There will be an initial current in this case. When the full voltage across that capacitor is applied to the resistor, there will be a current flowing. As that current flows through the capacitor, that means that the charge on the capacitor plates will be decreasing. There'll be a loss of charge because all of the charge that's flowing through the circuit is no longer built up on those capacitor plates. So as that current's flowing, the capacitor is losing charge. The change in charge in the capacitor plates is negative. But if the capacitor plates are losing charge, that means that the voltage across the capacitor is also decreasing. If that voltage is decreasing, that means that although there's still a push on that charge that's causing that current to continue to flow, that voltage is getting less and less. There's less and less of an impetus to push the charge through the circuit, and so although that current continues to flow, it flows less and less and less as time goes on. So we can see that there's got to be some time dependence to this circuit. Of an RC circuit, we have a capacitor connected to a resistor connected to a switch. There's also a battery and a switch on this side that are used to initially charge up the capacitor. Once the capacitor is charged, it doesn't really matter where that charge came from, how large of a battery or what you have connected to it. That energy is stored inside the capacitor, and when I close this switch, I'll have a complete circuit on this side, and this capacitor will be able to discharge through the resistor. What we have in the simulation, these little blue dots that represent the electrons. Remember that the conventional current assumes that a positive charge flows from the positive plate of the capacitor to the negative plate. In actuality, our charge carriers are negatively charged electrons, and so you'll see the blue dots flow the opposite direction as the negatively charged electrons leave the negative plate and move up to the positive plate. But if you have negative charge flowing counterclockwise, mathematically that's the same as our conventional current that we would think of as flowing clockwise. We're going to look at the current in our circuit here, the current flowing through the capacitor. And since we only are going to have one closed loop here, the current through the capacitor is going to be the same as the current through the resistor. We're also going to be looking at the voltage across our capacitor. And again, note that the voltage across the capacitor will be the same as the voltage across the resistor because they're connected in parallel in this case. So if we hit play on the simulation, we'll see that the voltage is fixed at 10 volts. That's the voltage that came from the battery, and so that's just a fixed value. The capacitor isn't connected to anything, all the switches are open, and so that charge is just going to stay on the capacitor. The capacitor voltage is going to stay at 10 volts. The current here is zero as well. There's no motion of charge because there's no complete path for that charge to move. So the current is 0. This 10 volts stored in the capacitor is connected to a 5 ohm resistor. And so what we're going to do is close the switch to connect our RC circuit, and we're going to observe what happens to the current in the circuit and the voltage. When I close the switch, notice that the charges immediately begin to move. You can notice a couple things here. I've hit pause. The current jumps from 0, it jumps up to 2 amps immediately, instantaneously, and then begins to fall away. The voltage across the capacitor is continuous. Once we've closed the switch, at the same instant, the voltage across the capacitor begins to fall because the capacitor is losing charge as that charge dissipates and flows through the rest of the circuit. Also notice that even though we're looking at the current up here and the voltage down there, these two graphs have the same shape. And if we let time go on, we see that the current goes back to 0 now that the capacitor is completely discharged. There's nothing pushing the charge through the circuit anymore. The voltage is 0 because there's no potential difference. There's no charge separation across our capacitor plates. When discharging an RC circuit, the instant that the switch is closed, the voltage on the capacitor is immediately applied to the resistor. And thus, when you have that voltage applied to resistance, we have an initial current flowing in that circuit. In this case, this is essentially Ohm's law, where the voltage on the capacitor is the same as the voltage on the resistor, because those are the only two elements in the circuit. In our simulation, we had 10 volts built up on the capacitor, and we had a 5 ohm resistance, and so we had an initial current of 2 amps immediately beginning to flow once the switch was thrown. We saw that instant where the switch is thrown, the current jumps from 0 up to that peak value, 2 amps in this case, and it begins dying off. As the capacitor discharges, as that current flows, the capacitor is losing charge, and so there's less and less voltage as the capacitor discharges, and as there's less voltage pushing charge through the circuit, there's less current flowing as a result of that current. We can use differential equations to treat this circuit and solve it directly, and what we find is that the current and the voltage, I have these equations here, where we have what's called an exponential decay. This is what an exponential decay graph looks like. This is what we observed in our simulation for the voltage across a capacitor. The voltage is going to start at some initial value. That's the initial voltage on the capacitor when it's initially charged from whatever voltage source it's connected to. As that capacitor discharges, it's going to have every single voltage possible from its initial voltage all the way down to 0. And so for an exponential decay, it's difficult to try to quantify what the voltage is because the voltage is taking on a changing array of values. And so what we do instead is we look at the time constant, which we call tau. For a RC circuit, the time constant is R times C. That's the equivalent resistance in the circuit multiplied by the equivalent capacitance. The voltage is always going to have this exponential decay curve, but you could have different shapes of exponential decay. You could have an exponential decay that looks like that, or an exponential decay that looks like that. When the time constant is very small, you have a very steep curve where the system reacts very quickly. When you have a large time constant, you still have the same general shape, but you have a much flatter curve where it takes much longer for the circuit to fully discharge. The way that we measure the time constant is to find when t equals tau, or whether find the point in time at which t equals tau, and your exponential term is e to the negative 1, which is about 0.37. So you look for when the value of the voltage, for example, falls to 37% of the original value. That should be one time constant. If you go 2 time constants down, that ends up being e to the negative 2 when t equals 2 tau, and so you should be at about 13% of your original value. And so you can look at what this graph looks like, how much time it takes to reach these various milestones, and you can figure out what the time constant of the curve must be. regardless of whether the time constant is small or medium or large, we notice that as t goes to infinity, the voltage and the current are both going to go to 0 because e to the negative infinity is going to be 0 no matter what. Have the same circuit where we have the capacitor that has been charged up by a voltage source, and now we're going to close a switch to look at the discharge of that capacitor across a resistor. The only thing that we've changed is we're using a digital voltmeter and a digital ammeter so that we can measure the numbers a little bit better so that we can try to figure out the time constant. In this case, we have a 0.1 farad capacitor and we have a 20 ohm resistor. So our time constant should be about 2 seconds. So what we're going to do, we're going to pause the circuit right now, and we're going to use a stopwatch, and that stopwatch is going to start as soon as we hit play. We said that one time constant has passed when the voltage drops to 37% of its original value. So 37% of 100 volts will be 37 volts. We should be at 2 time constants when we get to about 13% of the original value. In this case, 13% will be 13 volts. So we're going to hit play. We're going to watch the voltage. We're going to close the switch, and we're going to hit play and watch the voltage drop, and we're going to pause it as close as we can to 37 seconds. And we see that after about 2 seconds have passed, we're at 37 volts or so, a little bit below that because we went a little bit late. Then we're going to let it go a little bit farther down to 13 volts, 13%, and there it takes about 4 seconds. Again, that's 2 time constants. So our time constant is 2 when we have 0.1 farads and we have 20 ohms. When you take the product of 0.1 and 20, that's 2, and our time constant is 2. If I increase the resistance to 40 ohms, for example, I double it, and I charge the circuit. Now I can open the switch, and I'm going to do the same thing again. I'm going to pause the circuit. I'm going to close the switch, and again, when I hit play, I'm going to start discharging. Now that I have a larger resistance, I'm going a little bit more slowly. I'm still looking for 37%, just coming up. And so it takes about 4 seconds to drop to 37% of the original value. If I go, I'm looking for 13% is my next benchmark. And it takes about 8 seconds to go to 13% of my original value. So in this case, my time constant is 4 seconds. It took me 4 seconds to go from 100% to 37%. It took me another 4 seconds to go from 37% to 13%. In both of those cases, the time constant is the product of the capacitance and the resistance. In this case, 0.1 times 40 is 4 is our time constant.